Hello. So in our last set of videos during our remote learning, we had figured out how to do a right sum as well as a left sum in MATLAB. Okay, so we were looking at a function, like in this case, we have the function x squared plus 4, and we were trying to find the area under the curve between x equals 1 and x equals 4. And in the picture you see right now, you have the left sum being shown. But if we change the sum type to 2, you have the right sum. And so we can see clearly with 6 subintervals, the left sum rectangles give us areas that are under the curve, meaning there'll be less area added up using the left sum than if we were to take the area under the curve and above the x-axis between x equals 1 and 4, whereas the right sum was above the curve. And we could see the answer for the area under the curve is somewhere between what the left sum and the right sum gave us. We also saw that if we were to increase the interval number, so let's go from 6 to 12, and we do it again. The difference, the left sum gives me 31 and a little. If I turn that around and do the right sum, you can see the answer is 30, almost 35. So the real answer for the area under the curve is somewhere between probably 31 and 35. And we can see with 12 subintervals, the right sum has extra corners over the curve, but those are relatively small now. And if we were to go out to, say, 24 instead, those differences get even smaller. All right. So let me go back to an n value of 6. All right. If for some reason you did not have working code that can do all of those things, right, you can, I'm going to scroll down in my code to where the right sum was computed. And you probably want to copy that in there. Let me highlight a few things first, though. Okay. So remember what we did. First of all, we created a linear space for all of the points on the blue curve. Okay, or thousands of them. Okay, there were 5,001 points, and we are connecting, in 5,000 steps, we connect all the blue points, which gives us a very smooth blue curve. All right, so that's what x1 is used for, and y1, it's all the points for the blue curve. All right, but if we want to make our rectangles, we need to have x and y values at the ends of each subinterval. Okay, so this line of code right here is going to start us at the a value. That's the left-hand side of where we're trying to add up the area, all the way to the b value. And since I want 6 subintervals, we needed 7 vertical lines at 1, 1.5, 2, 2.5, 3, 3.5, and 4. That's 7 vertical lines. All right, and we need the y value at the top, where those vertical lines intersect the curve. Since this is the right sum, we don't use the first x and y value in computing a rectangle. Well, actually, we'll use the first x values, but we never use the first y value because we're finding our y's at x equals 1.5. When we do the left sum, we would start with 1, but then we would leave out what happens at x equals 4. We would leave out the y value over on the far side. Okay, so what do x2 and y2 end up doing? Those give us all of the points that we need for the corners of the rectangles. All right, so there are fewer points that we need. We only need 7 of them in this case for drawing our rectangles. All right, then we computed how wide each rectangle is. That's really a delta x, but dx is the best we can do in MATLAB. So we divide the interval by the number of subintervals to get the size of each. Then there are a few lines of code to just make sure that we include all of this code. Just make sure that when we go to graph it, we will in fact include the x-axis. So if you'll notice the blue curve, all the points are positive. If I didn't have this adjustment code, when I do the graph, we would end up having the bottom of it over here at 4 point something instead of all the way down at 0. Since we want the area between the curve and the x-axis, we need to make that adjustment so we can visually see it. If they had all the points had been negative, the reverse would happen. That's what line 32 to 33 deals with if all of the values are negative. 34 to 35 deals with adjustments if all the values are positive. And I'm sorry, no, I got that backwards. 33 deals with all the values being positive, and 35 deals with all of the values being negative. So that's just for graphing. Then the plot statement starting in line 38 plots the curve and the x-axis. And it does that. Let's see. Oh, and the y-axis as well. So this plots the blue curve and the x and y axes in black. In this case, we don't see the y-axis because the left side of the graph is at x equals 0 already. But those would, second two lines of the plot statement, this one gives me the first one gives me the x-axis, the second one gives me the y-axis. Continuing down, then it gets tricky. This is where we want to plot our rectangles, right? And case 1 is what I gave to you. And case 2 is what you should have coded in to the original code in order to generate a right sum. So we talked about in the previous video how this plot statement gives me all of the x values for the corners of the rectangle, followed by all of the y values for the corner of the rectangle. If I'm doing a left sum, I'm picking the y value, just for the first rectangle, I'm picking the y value at the left side of each of the rectangles. That's what y2it would give me. But for the right sum, y2 of it plus 1 will be the next side, which would end up being the right side for each of the rectangles. Okay, so this is all review, hopefully. And you'll notice that when we go to find the cumulative area, for the right sum, we use the y value at the right side, whereas for the left sum, that represents the y value at the left side, okay? So remember that the left side is at it, and the right side of each interval is at it plus 1, right? So now we're ready to add 2 more cases, right? The easier case to add is the trapezoidal case. So what I'm going to do, I'm going to copy the right sum. And everything that's in the right sum, I am going to include, let's see, okay, that would be there, okay, the 4 IT, okay, yes. So I have the whole right sum copied, and let me paste it. And let me re-indent that properly. So I can highlight all the code, and if I use Control-I, it gets my indentations correct. You can also indent up here, and you can get your indentations to work properly, but Control-I is nice for getting that to happen. All right, now this is not case 3 anymore. We already had case 2. I'm sorry, it's not case 2 anymore, which is why it was underlined. It is now case 3. And let's make this a trapezoidal sum. Okay, so the trapezoidal sum uses the left side and the right side to draw the top. Okay, so it uses the y value at the left side and connects it to the y value at the right side to produce the top. So when I go to do the plot, I only need to make one change. The first y value is down at the bottom of the rectangle, so that's still 0. But the second y value should be the upper left-hand corner. But now we're going to use the left-hand value there. So instead of it plus 1, which was the right-hand value, you will drop it back to it. That's the left-hand value. But for the third point, we do want to use the right-hand value, which is it plus 1. And the fourth point is back down to y equals 0. So this one little change should give us a slanted top. All right, let me run that real quickly so you can see it. Whoops, oh, I didn't change my case to case 3. So in my plot choice, or what did I call that? My sum choice, type, I'm sorry, I called it type right here. I want to change this to a 3 now. And we can say over here that 3 equals, we'll just call it trap for short. Okay, and we're going to later have 4 is equal to midpoint. Okay, so we'll call that mid, right? So for type 3, let's go back down. Now it's on type 3. And you can see that we have slanted tops that connect the left and the right side of the subintervals. And those shapes are trapezoids, okay? You're used to seeing a trapezoid horizontally, where you have a top and bottom. Yeah, if we turned each one of these shapes on its side, it would be what you're used to seeing as a trapezoid. So we have sort of vertically aligned trapezoids, where the two vertical sides are the bases, and then we have a width for each one that's constant across the whole trapezoid instead of a height like you're used to for a trapezoid. Now, what does that top do? Well, it averages. The top cuts right across the difference between the right hand and left hand sum. Okay, so you may remember that to get the area of a trapezoid, you average the length of the bases times the height. Well, in this case, since it's a vertical trapezoid, to get the area, we need to average the lengths of the heights, okay, and then multiply that by the width. So you can see we almost have that here. We have the height at the right-hand side, and we're multiplying that times the width. Well, what we need in the highlighted area is the average of the height at the right-hand side and the left-hand side. All right, so let's do that right here, right now. So to average two things, you can multiply them by 0.5. You can multiply the sum of two things times 0.5. Okay, now what am I going to have to average? I'm going to notice I just put another parentheses in. I will need to have y2 of it plus y2 of it plus 1. We sum those up, multiply by 1/2, and then multiply that by the width. So this line of code here is what you need to get the area. So if you haven't coded in yet, you can pause the video right here. Make sure that you add in your code. You can switch over to your code. Make sure that the comment next to the types has been expanded to include 2 more types. And do case 3. So you could pause the video right here and type in what you see. What I hope is that you understand why it works. So we use the left side and the right side heights, and then we use an average of the left and right side heights times the width in order to get the areas. All right, so if I run this again, it will give me the correct area for the trapezoids. Before I ran it, it was still on the right sum. Okay, oh, and now I need to change this. This is the trapezoidal sum. Okay, so that will change in the title. All right. So once you have that in, you can restart the video, and then I'll talk about the midpoint sum. All right. So the midpoint sum is a little bit trickier. We need new x values. And I'm going to create these based on x2. Okay, so we already have all of the left and right sides in x2. In order to get the midpoints, I simply need to shift those over by 1. Okay, I'm sorry, by 1/2 of a width. And right here in the code in line 29, I've programmed in the width. So I can now create an x3. Okay, so I'm going to generate midpoints. So the first thing I'm going to do is I'm going to create an x3. okay, will equal, and then let's do this. Let's say it will equal the x2 values plus dx divided by 2. Okay, so it will give me all of those. Okay. Now it's going to give me an extra midpoint kind of hanging off of the end. So in this case, the extra midpoint would be at 4.25. We'll just generate it and then ignore it later when we get to the loop. So that's what the x3 values will be. They'll just build right on to what the x2 values were. All right. And now we'll do what we did before. We have to put those into x for the in order to be able to evaluate and get the y values at those midpoints. So we will simply store those in x, so then we can find a y3 that will be an evaluation of the function. Okay, and since the function used x as the variable, by putting x3, storing it in x, these y3 values will be at all of those midpoints, with an extra one out at the end. Okay, so that's all we need to do to generate the midpoints for the rectangles. Now, let's come on down here and figure out how to plot those. So I'm going to reuse my right sum. So let me use case 2, copy it, come down and paste it. And let me say, okay, so I probably want to put another space in here. Once again, let's highlight it and can use Control I. So right away we can see the 2 is underlined because we're moving on to case 4. And we can write midpoint sum. And now let's edit this all the way down. Okay. So when we edit this, let's see. Here we go. This is, we're going to plot, not x2. Actually, we are going to use the x2 values. I'm sorry. When we go to do the rectangles, the left and right sides are still at the same locations. What's different is the y side. This is going to be y3. Okay, so this is y3, and actually we can go back to it. Remember, y3 is the height at the middle of the subinterval. Okay, so let's see what happens if I plot this. I think we might end up with one extra rectangle. Let's see. Oh, and I never changed the type. It's still giving me the trapezoidal sum because I never changed the type. So let me change that to a 4 and come down here and see what happens now. Sure enough, it worked. Okay, so we're going to go from 1 to n. Oh, because we only have 6 subintervals, it simply ignored the 7th y3 value. Okay, so it worked because since n equals 6, it plotted these out for the first 6 midpoints, and those would be the rectangles that have where the height is taken in the middle. Okay. Now, obviously, for that we need the area in the middle. So I need to get rid of the +1 because we want to use the middles at 1 through 6. We want to ignore the 7th middle. And so that will give me the area of those rectangles. This is now also, we keep on going down. When you cut and paste, you need to be carefully edit line by line. And this is now the midpoint sum. All right. So there you have it. That's how you do the midpoint sum. You need to generate the midpoints. They're new x values. They weren't in x1. They weren't in x2. So we needed to create a new x3 in order to get the midpoint x values, and then we could find the y's at all of those x values. All right, so if you need to program that in, you can pause the video and then put the case 4 code in for your midpoint sum. We now have all of the answers, right? Now, I just want to quickly talk about over and underestimating. Okay, so right now we have a function that is increasing and it is concave up. All right, so if I were to look at the left sum, switch back to type 1, it is under the curve because the left side of every rectangle is the lowest possible function value on the subinterval, right? So we're trying to estimate the area under the curve by using the lowest possible function value at every single x input that we use. The left side is always the lowest side. So we're guaranteed that that will be under the curve, right? If we were to switch to a right sum, the right-hand side on every subinterval is always the highest possible value that we can use in finding the area of the subinterval. So that will estimate. Now, the left is the lowest because this is an increasing function, and the right is the highest because it is a strictly increasing function. For every subinterval, the left side is the lowest point and the right side is the highest point. Now, it's emphasized even more clearly if I make my n value smaller, it exaggerates it even more, okay? Now, let me switch over to the type 3, the trapezoid. And let me actually make n equal 2 to exaggerate this even more. Okay, so we can clearly see when we're looking at this, and I could even further exaggerate it by making x max stop at, say, 4.5, and let's look at it now. Okay, so we can see the red line is over the curve, so the trapezoidal method overestimates this, okay? It overestimates the area, I should say, all right? Now, why is that? It's because the curve is concave up. It's not because it's increasing, right? If I were to do the same thing with, say, the square root of x, so SQRT of x, we can see that the trapezoidal top is under the curve instead of over the curve. Okay, so the way the curve is bowing determines whether the curve will be over the straight line connecting the 2 points, which is the top of the trapezoid, or under it. So when it's bowed to be concave up, the trapezoidal line, which is a secant line between 2 points, is over the curve. When it's bowed downward, okay, and it's concave down, then the trapezoidal line will be under the curve. Right, so we can see in this case, actually, let me go back to the function we had, was x squared plus 4. The area under the trapezoids is actually relatively close to the area of the curve. There's only a small difference, but it is coming out to be 34.125. We know that that answer is too high, right? Now let's switch over to type 4, which would be the midpoint method. And it's not clear, but when you look at the value, you can see that that value is lower than what it had been. So this estimation is always going to be the opposite of the estimation of the trapezoid. So when the trapezoid is too high, the midpoint sum will be too low. Okay, and when the midpoint sum, when the trapezoidal sum is too low, the midpoint will be too high. Now it's kind of subtle here, but you can see where my arrow is right now. That's the area that was left out of the first subinterval. Okay, over here is extra area that was included by the rectangle that isn't under the curve. if you look closely, you can see that the area, in fact, let me make this figure much bigger. It becomes fairly clear that this extra area here exceeds the missing area. I'm sorry, I should switch that around. This area over here on the left side is extra area included by the rectangle. But over here on the right is area that was missing from under the rectangle. The area over the curve on the right exceeds the area that's the extra area included under the rectangle on the left. So we're missing too much area, which is why this is low. So overall, the value comes out to be a little bit low. In a previous video, I mentioned that if you were to slant the top of the rectangle right at the point of intersection with the line, we could slant this until it is a tangent line, in which case you could clearly see that when the curve is concave up, the tangent line is below the curve. And so that explains why the midpoint is going to underestimate when the curve is concave up. Whereas if we switch to the square root of x, let me go back to that. The midpoint method will give me too much area. It's a little bit hard to see, but the extra area under the rectangle here, in this case, will now be more than what we are missing over here. You have to look very, very closely to see that. In fact, if I did this with one subinterval, maybe it becomes more apparent. So let me do n equals 1. And this extra area here is bigger than this area up here that's missing. It's still not obvious when you look at it, but that will be the case because it would be the same as if we took the area under the tangent line. And the tangent line in the middle is clearly going to be over top of the curve. So that in this case, the midpoint sum would overestimate the total. Okay, so make sure you have all the code in place so that you can then write down, make your tables for homework, just to try the various sums with a couple of different functions and relate that to using the antiderivative. Okay, so have fun with that, and I will see you on Thursday.